Stripping down science. The Naked Scientists.
Hello, welcome to this week's Naked Scientists with Phil Rosenberg.
Hi.
Dave Ansell.
Hi there.
And I'm Chris Smith. Now, this week, putting the brakes on car accidents, scientists have come up with a much better way to warn motorists when the car in front is stopping. And on the subject of pile-ups, NASA have a new way to avoid cosmic collisions between the Earth and nearby asteroids. We'll be finding out about that later. Plus, how pollution is turning mountaintops into virtual deserts as the rainfall declines. Find out why.
Also this week, pollution in your petrol. As some major retailers admit that supplies were contaminated, we'll be finding out what caused thousands of cars to grind to a halt. Plus, we're bringing you the lowdown on the Cambridge Science Festival, which kicks off next week.
And this week we've got a great kitchen science experiment for you to try. We'll be showing you how to see the invisible. All you need is some vinegar, some bicarbonate soda and a torch. Find out how it works in a few minutes' time.
And if you're in the mood to win some stuff, then this week we've got the most incredible prize. We've got 2 tickets for you to go and see Al Gore. That's the real Al Gore who ran against President Bush in the recent US elections. He'll be talking on March the 26th in Cambridge about the inconvenient truth. That's the story of climate change. Or if you'd rather, and you don't want to go and see Al Gore, we'll dig you up a mud-powered clock, I should think. To win it, can you tell us, if we replaced the sun with an electric bar fire, how many 1 kilowatt bars would it have to have in order to match the present energy output of the sun? And obviously it's going to be the closest answer that's going to win it.
The Naked Scientists podcast, powered by UK Fast, the UK's best hosting provider, on the web at ukfast.net.
Now, interesting, if you look at the number of accidents that happen on the roads, what's the most common reason that one car crashes into another? Well, at least a third of them, so particularly common, are rear-enders, literally one car bashing into the back of the other one because the driver didn't notice that the person in front of them was going to stop. Part of the reason, researchers think, is because brake lights don't really tell you very much about the car in front of you. They just tell you that someone has touched the brakes. They don't give you any information whatsoever about how hard someone's braking. And that occurred to two researchers at the University of Toronto who are called Zhonggai Li and Paul Milgram. And they thought if we redesigned the lights in the back of a car, perhaps we could make it far easier for people to be able to see what's going on in the car in front and therefore react more quickly. So the idea they've come up with is to have lights that not only get bigger when you press the brake for longer, but they also move across the back of the car. So they've got this triangular configuration of light bulbs, and as you press the brake for longer and for harder amounts, so you press it down more firmly, then the brake lights get larger and they move laterally from the middle of the car towards the edges. Now, they've tried it in a simulator with 40 drivers, and they found that it did make a significant difference. So there were big kind of improvements in driving safety when the driving conditions in the simulator were at their poorest. In other words, there was bad vision conditions or bad road conditions for other reasons. So this could be a very simple and easy thing to implement, which would actually make the roads a hell of a lot safer.
Does that mean that your brain will think that the car's closer than it actually is because the lights are getting wider?
Well, part of it is that people may not notice when the car in front brakes because the brake lights are a fixed thing in one position on the back of the car. And if you're just not looking in that direction, they don't, what we call, subtend a very big area on your retina. So if you have a moving stimulus, we know that the brain is really exquisitely sensitive to things that move because it's much more attuned to picking up movement than it is static things. And because these things are not only moving, they're also getting larger, this should also have a sort of double-edged message to the brain, hey, react more quickly, and this should make people put the brakes on sooner and therefore avoid some of these rear-enders, because telling people leave a 2-second gap between you and the car in front just doesn't seem to work, because we know that huge numbers of accidents happen that way.
Well, from road collisions to space collisions, now we're going to look at a report that NASA have just released this week on how we should look for killer asteroids. These are asteroids that are going to be on a collision course to Earth, kind of like on the Hollywood blockbuster Deep Impact. Now, basically, the problem is that space is a bleeding big thing. It's really huge, really massive, and asteroids are really piddly, so they're really difficult to actually find. And asteroids just turn up quite randomly that only just miss the Earth, and we don't spot them until they're whizzing past. And that's a real problem, and we do think that these sort of events could be really disastrous. If we get a big asteroid that hits the Earth, they're very rare events. I mean, for example, an asteroid that's bigger than 10 kilometres, the Earth gets hit about once every 25 million years by an asteroid like that. But the effect of something like that would be absolutely disastrous. It would demolish a continent almost, really have worldwide effects of earthquakes, tsunamis.
Well, we've seen the dinosaurs disappear because of this, haven't we?
Absolutely. And on smaller scales, these things get much more frequent. We had an impact just at the beginning of the 1900s by something about 10 metres across. So a fairly small asteroid, really. And it basically wiped out about 2,000 square kilometres of Siberian wasteland.
Was this the Tunguska
Yeah,
event?
absolutely. And it just wiped out 2,000 square kilometres of forest, just laid it completely flat. And these sort of events happen about once every 250 years. I mean, if that had happened over London or somewhere like that, then it would have been a real disaster. You know, millions of people would have ended up dead from an event like that.
Has anyone actually ever died because of being hit by a meteorite? Or
There's currently no claims of anyone ever dying. There's actually a slightly, I say a spoof report. It's one of these things that is banded around and no one's ever quite sure how true it is, that a dog was once killed by an asteroid. It's actually a bit of Mars that fell into the Earth's atmosphere. It'd been blasted off Mars and landed on Earth, and it hit a dog apparently, but no one's quite sure how true that is.
Because there was a guy who, was it a lady, had their car written off by a meteorite, and it was actually worth a lot more afterwards than it was before, because it made all the newspapers, and then people were eager to buy it, because, you know, first car written off by a falling piece of space debris.
Absolutely, and that same asteroid actually was viewed from a baseball stadium, passing over the baseball stadium. Someone was videoing the game and saw this asteroid passing overhead, or this sort of shooting star passing overhead, and filmed it going down. And it went through someone's roof and into their garage and smashed the car.
There's another unfortunate incident of a chap, I think he was in America, where he had just spent a fortune renovating his bathroom, and he went out to the shops and came back, and his bathroom had been completely destroyed by what amounted to, eventually was found to be a meteorite impact. And the funny thing was that it was the bathroom that got laid waste, and this guy's name was Mr. Fawcett, which of course is worth a tap, isn't it?
In America. So basically, NASA have now looked into the best way to do this, to actually look for these asteroids, because we really don't know how many there are out there. We think there's probably about 20,000 asteroids bigger than 140 metres across. Then that sort of size would wipe out a city. And we just don't know where they are. Now, the best way they've found to do it is actually to put a space telescope, kind of like the Hubble telescope, somewhere near Venus. Now, the reason why they put it near Venus is because these asteroids can come sort of from the direction of the sun, and we can't see them, kind of like a fighter pilot coming in to attack from the sun. You kind of get, it dazzles the sun.
So how do we spot them? We just look with
basically,
telescope.
you have a telescope that just remotely just scans across the whole sky and looks for these things, and it just needs a dedicated instrument to do that. Unfortunately, this sort of thing is going to cost about $1 billion, which is quite a lot of money. But if you consider the fact that this sort of thing could save, well, maybe the human race, who knows, or, you know, millions and millions of deaths if one of these things gets spotted on a collision course, then it could be really worth it. Unfortunately, at the moment, the budget's just not there, but we'll keep our fingers crossed that this next asteroid isn't on its way already.
It's quite interesting you're talking about that, because there was a paper in the journal Nature this week by a guy called Mikko Kastelainen from the University of Helsinki, and they've been looking at this particular asteroid called Apollo. It's not very big, it's about a mile across, so 1.5 kilometres in diameter, this asteroid, and they've been watching how it turns and spins, because most of these bits of space debris are continuously rotating, and they noticed that some of their measurements just don't add up. In other words, it seems to be turning at a different rate than it should if it was just spinning in the air. And what they've found is that this is subject to something called the YORP, Y-O-R-P, the YORP effect. And the reason it's called the YORP effect is because, and try saying this when you've had a few, it's the Yarkovsky-O'Keefe-Radzievsky-Paddock effect. Now, what this means is that when light hits something, it gives it a little push. And if something is an irregular shape, then it ends up being pushed a little bit harder when it's turned one face towards the sun than when it's turned around a little bit further. And this, of course, offsets the spin and starts to change the direction of movement of the object. And it's only a fraction of a second, about a 1/4,000th of a second every year, but over a long time it adds up to quite a significant amount of deviation in the course of this object. And what you've been saying about detecting these things when they might be on an earthbound course, well, this is a strong enough effect to push certain objects into the path of the Earth's orbit, so it could actually create trouble for us. But also it may hold the solution, because people have speculated that if you were to put a reflective coating on one surface of an asteroid but not on the other, then it would get more of a push in one direction than the other, and this could actually push it off of an earthbound course.
So we could literally go out there and paint the asteroid a different colour to work it out.
Laying the facts bare, the Naked Scientists.
On a completely different subject, some researchers have discovered that pollution is affecting rainfall in mountainous areas. And normally in a mountain it rains a lot because humid air is blown against the mountain, it rises, it cools, condenses into little drops, and those drops join together to make bigger drops until eventually they can fall out of the cloud as rain. Now, Daniel Rosenfeld from the Hebrew University in Jerusalem has been studying the rainfall on Mount Hua in central China, which is apparently a very important religious mountain for the Chinese. And as pollution has increased, the mountain seems to have got less rain compared to the plains 15 or 16 kilometres nearby. Now, they reckon this is because when you have pollution, you've got lots more dust and pollution in the sky. And this means there's more places for the little raindrops to form when the water starts to condense. So instead of having a few bigger drops, you have lots and lots of smaller ones. So it takes much longer to join together into something big enough to fall out of the sky as rain. So instead of getting lots of nice rain, you just get a bit of mist. And by the time it's had time to do it, the air's come back down again, and it's warmed up and it's all evaporated. And apparently this could be a big problem for areas that are dependent on mountain rains, like Egypt and places where it's all coming based on irrigation. And so something which needs a lot more study.
Someone in China was writing in a magazine recently saying they'd been to a fairly remote place, quite mountainous, and there used to be a well sort of 3/4 of the way up this mountain, this village, and the villagers had no problem with water for, well, the village has been there thousands of years, and fairly recently they've said they're now having to lower such a long piece of rope down that it's actually more worthwhile to go elsewhere for their water, and the place is drying up, so that could be the manifestation of that, because China's air quality is terrible, isn't it?
Yeah, because all their power's, an awful lot of their power is being generated from coal, which is a very, very dirty source of
One
power.
new coal-fired power station a week. I was looking at the figures because, of course, Beijing is the host city for the next Olympics. And a major problem with that is that at the moment Beijing only has air which is viewed as fit for human consumption about 280 days of the year. So if you're trying to run when you can't even see the other end of the stadium because of the smog, you're not going to see many Olympic records broken there, are we?
It's not going to be a good one, is it? OK, well, from dust in our atmosphere to dust in space again, back up into the outer space. Basically, this is a problem that astronauts are going to have when we get back to the moon. A team at Stony Brook University in New York have been investigating how moon dust and Martian dust are going to affect astronauts when NASA eventually go back to the moon. They're aiming to get back to the moon by 2020 and actually get astronauts on Mars by about 2030 or maybe a bit later. And basically what they've found is that the dust, because it's so fine-grained on Mars and on the moon, when you inhale it, it gets wet in your lung. And actually what they found is when you mix water with this dust, they've mimicked it with Earth meteorite, or Earth rocks, ground it up into this fine powder. What they've found is that it actually produces hydrogen peroxide, and it's just a chemical reaction with the surface of this dust. And, you know, hydrogen peroxide is the same stuff you use to bleach your hair.
Because everyone would go blonde on Mars, wouldn't they?
Well, except for the fact it's in your lungs, so it's
but
not
surely
a good place to...
people are using respiratory equipment, aren't they? So there's no atmosphere on the moon, there's no appreciable atmosphere that we can breathe on Mars, so why would this be a problem?
Well, basically, yeah, you're right. You're in your spacesuit, walking around on the moon, you breathe in bottled air, essentially, same as a diver would do. But then once you go back into your lunar capsule or your Mars capsule, you've got all this dust that sticks to your suit and sticks to your boots and gets everywhere. And basically, you traipse it all inside, just like mud on the Earth, and then it gets into the atmosphere in your lunar capsule, and you're breathing it in all the time. So really, they're looking to sort of ways to try and counter that and then get rid of it. So maybe they'll actually wash you with an air shower before you get into the capsule, so you'll blow air at you to brush all this dust off. Possibly even use liquid carbon dioxide.
Sounds very nasty. You're listening to The Naked Scientists with Chris, Dave and Phil. It's our science Q&A show, which we do once a month. Coming up shortly, we'll be finding out what triggered the fuel crisis in the southeast of England. Why did lots of cars grind to a halt? What was the contaminant in the fuel that made that happen? We'll also be giving you the lowdown on the Cambridge Science Festival, and later on in the programme, finding out how scientists have managed to turn tiny marine algae, which have got silicate in their shells, into silicon replicas of those organisms, and then turn them into an amazing series of gas sensors. That's all on the way.
The Naked Scientists, supported by the Wellcome Trust.
Got a question here from Matthew in Southend-on-Sea. Says, I'm a new listener, I love your show. When a meteor hits the Earth, like the one that was supposed to have killed off the dinosaurs, it hit with the impact of hundreds or even thousands of nuclear bombs going off. Why was that? Because if I was to throw a large rock off, say, the Empire State Building, it would make a big crater, but no fire, no explosion, no nuclear reaction. Why is this then?
OK, well, when you actually have a meteor or an asteroid hitting the Earth, it doesn't create a nuclear reaction. It's literally just the energy from the speed that it hits. If you drop a stone off the Empire State Building, it'll probably hit the floor at a few metres per second. When an asteroid comes in, hits the Earth, it's coming in at probably maybe 20 kilometres per second. Incredibly fast, what we call hypervelocity. Incredibly fast. And that energy from such a massive object, you know, it could be hundreds of metres or even kilometres across, hitting something and basically gets stopped dead. All that energy from the speed it was going at gets immediately converted into heat or sound waves propagating through the crust of the Earth. And it can do immense damage to the Earth and basically blast vast amounts of rock and debris up into the atmosphere, which can cause climate change and all sorts of nasty problems.
Thanks, Phil. Dave?
For this week's Kitchen Science, Derek and I went to Castle Manor Business and Enterprise College in Haverhill to help Terry and Ellie, who are both in Year 11, to see the invisible.
Hello there, welcome to Castle Manor Business and Enterprise College in Haverhill, where we've come today to do some excellent science experiments with, of course, Dave, who is here. So what is it we're doing today, Dave?
We're going to be trying to see the invisible with just a torch.
OK, so we're going to be seeing the invisible, and if you want to try this at home, then you can do so. Just keep listening, and I'll be telling you what you need very shortly. Also, from the college here, we've got two helpers who are going to do the experiment for us. So could you guys tell me your names and what years you're in, please?
I'm Terry, I'm in Year 11.
And I'm Ellie in Year 11.
All right, thanks for coming down, guys. And also, could I just quickly find out, because we're going to do some science, what is it you guys like about science, if anything? Terry?
Lots of things.
All right, anything in particular, any particular subject you like?
Biology.
All right, OK. And yourself, Ellie?
I like doing the practicals in chemistry.
All right, OK, and I think this actually might suit you then, basically. So Dave's nodding. OK, very good. So, Dave, we're going to do this experiment, but firstly, if you'd like to do this at home, then this is what you need, basically. The first thing is a pint glass. Secondly, some vinegar or lemon juice, basically, some kind of acidic liquid, basically, but vinegar works absolutely fine. Some bicarbonate of soda, OK, and you'll need a few tablespoons of that, or even a few teaspoons would be all right. OK, and then you need a torch, and we'll explain how you set up that torch in a minute, and also a white wall, a bit of a wall that is white, or a bit of white paper will be fine. OK, so Dave is going to instruct Terry and Ellie how to do this, so what do they do?
Well, the first thing you're going to need later is a torch, which you can take the reflector off. So you don't want that shiny mirror-y thing in the torch. You want somewhere taking that out, so you just see the bulb.
OK, so yeah, so you kind of screw off the actual bit of plastic that's kind of transparent that the bulb shines through. Got you. OK, now, what do we do to set this up?
Well, first of all, you take maybe a tablespoonful of bicarbonate of soda and put it in the jar. Could you do that for me, Ellie?
So basically, we don't bother with spoons here, do we? We just basically pour it straight in.
That'd be about right.
How's that? Good. OK, right, and next?
OK, and then, Terry, if you'd like to take some vinegar, maybe pour centimetre and a half of vinegar in there.
OK, and tell us what happens as well.
It starts to fizz.
All right, OK, and I don't know, is that enough? How much do we want?
You basically want the fizz to have filled up the whole glass once.
All right, so let's whack a load more in, basically. OK, oh, is it going to... Oh, no, we've managed to make it overflow slightly, but we don't care. It's all right, we'll clean up. Now, what's going on there, Dave, basically? Why is it actually fizzing up?
Well, in the bicarbonate of soda, locked up really tight, there's a gas called carbon dioxide. You may have heard of it. It's the stuff you breathe out. And when you add the vinegar, it releases that carbon dioxide, and the carbon dioxide is much bigger than the bicarbonate of soda, so it expands lots and makes loads of foam.
And at this point, there's also a bit of a whiff, isn't there? What does it smell like, Ellie?
Vinegar.
Yeah, it's kind of like vinegar, but worse, isn't it, really? It's like if you put vinegar on your chips and then just imagine it's gone off for a long time, something like that. So there you go. But anyway, notwithstanding the smell, it's still a very cool experiment, so do keep pressing on. So what do we have to do with this, Dave?
Well, then what you want to do is take the glass, imagine it's full of a liquid, because it's going to be full of this carbon dioxide, take it up near your white wall or white piece of paper, shine the torch at it, and then just pour, imagining it was full of something, and see what you can see.
OK, so what you've got to do then is take that pint glass, which you're imagining is full of liquid. Of course, it's not. It's only got a bit of liquid in the bottom, but you're imagining it's totally full of liquid because it's actually full of this gas, carbon dioxide. And then you're going to hold the torch near the wall. You're going to kind of have a vague beam of light going onto the wall or your white surface or whatever. And then you have to pour that imaginary liquid through the light, basically, and see what effect it has on the light that is cast on the wall. And if you actually switch the lights off in the room that you're in, then this should make it much easier for you to see. OK, so the question is, we're going to do this later in the show, so we'll be coming back here to Haverhill to find out what happens. But Terry, what do you think might happen?
Don't have a clue.
All right, OK. Ellie, any idea?
No idea.
OK, we've stumped them there, so there you go. Well, if you at home are stumped, then why not try it yourself? And if you can get the answer, then please do give us a ring. It's 08459 25 2000, and you can also email chris@thenakedscientist.com. So there we go. We'll be back here in Haverhill later on in the show to find out what happens with Terry, Ellie and Dave, and until then, it's goodbye.
So if you want to have a go at that, all you need is some lemon juice or some vinegar. Pour a bit of it onto a load of bicarbonate of soda in a cup or beaker, then dim the light, tip up the beaker and shine the torch through the imaginary stuff you're pouring out, and have a look and see what you can see on that wall.
If you want to have a go at this week's teaser, the teaser is, if we wanted to replace the sun with an electric fire in the sky, how many 1 kilowatt electric bars would our notional electric bar fire have to replace or match the present energy output of the sun? What have we heard from so far, Phil?
We've had a few guesses ranging from 25 million all the way up to 10 to the 25 bars. So that's 10 with 25 zeros on the end. So and 1 trillion has been a guess by Valerie. Nigel Lorden has got 10 to the 20, which is 10 with 20 knots on the end. And Connor, 10 to the 25, 10 with 25 knots on.
Sorting out the sparks from the quarks. The Naked Scientists.
Now it's time to cross the Atlantic with Bob and Chelsea to find out about new ways to treat viral infections.
This week for The Naked Scientists, the past and the future of treating infectious diseases. I'm going to talk about the next generation of antiviral drugs, but first, Chelsea is going to share some of the lessons learned from polio in the U.S.
Since 1955, America has spent $35 billion on polio vaccination. That might seem like a lot, but that spending has generated a net savings of over $180 billion. That's according to a new analysis by scientists at the Harvard School of Public Health. Lead author Kimberly Thompson says they modeled how the disease would have spread without vaccinations and then estimated how much it would have cost to treat it.
People often don't realize that it's hard to get credit for things that don't happen. This is a real challenge because with respect to public health, if people don't see the benefits of the interventions, but they look at the costs, then they might misperceive, in fact, how very valuable public health interventions are.
She says that's an important lesson not only for efforts to eradicate polio in developing countries, but also for healthcare systems in developed countries, where emergency treatment often trumps preventive care.
Thanks, Chelsea. A new kind of drug may fight viruses and other causes of disease by silencing their genes. The key ingredient is small interfering RNA, a molecule that can block specific genes from making proteins. Judy Lieberman of Harvard Medical School says such drugs would have broad potential.
Since the machinery for RNA interference exists in all cells, this natural pathway can be used to silence any gene that might be involved in disease.
In animal studies, Lieberman's team found a way to get interfering RNA into infected cells without affecting healthy cells. Now she and her colleagues are working on RNA therapies for a respiratory virus, pandemic flu, and even high cholesterol.
Thanks, Bob. Next time we'll talk about how global warming could break up some happy symbiotic relationships. Until then, I'm Chelsea Wald.
And I'm Bob Hirschon for AAAS, the Science Society. Back to you, Naked Scientists.
Bob, Chelsea, thanks very much.
And you can find out more about Science Update on their website at www.scienceupdate.com. Got an email here from Nick, and this is for you, Nick. Because Nick says, "Hi, could you please consider using a slightly different sound than the My Doorbell for the correct quiz answers? Listening half asleep during the night the other day, it caused me to answer the front door to no one in my underpants."
Oh dear.
So anyway, just in case you missed that, Nick, we'll be returning to that shortly. Now, Dave, got a question here from Stephen Lawrence, who is from the Committee for Future Energies in Cambridge. This is an interesting one, this. Wonder what you think about this. He says, Dear everyone at The Naked Scientists, in an energy-saving frame of mind, I've always wondered whether it would be possible to build an alternative to conventional thermal tumble dryers. Would it be practicable to build basically a large vacuum chamber, put the clothes inside, pump the air out, and therefore lower the pressure, and that makes the water in the clothes boil or evaporate off? Would the clothes survive the experiment, and would it be energy efficient? Would the whole thing cost so much that it would just be uneconomical? What do you think?
It would certainly work. Drying things by evacuating them definitely works. It's how chemists dry chemicals quite often, and it's how you freeze dry things like coffee. To be honest, I don't know quite what the thermodynamics and whether you're using more energy that way or less energy than you would by just burning gas and heating it up. So I'm not sure.
So if anyone can help us with that, I guess, it'd be quite interesting to know. And maybe there's the scope for a future kitchen science experiment. Has anyone ever tried drying their clothes in a vacuum chamber? If you've tried this, let us know. If you've done the maths and can work out whether it would be easier to dry your clothes in a vacuum chamber than using heat, please let us know on The Naked Scientist, chris@nakedscientist.com. Now, earlier this week, there were a whole number of retailers who admitted that stocks of their petrol had been contaminated with something that had caused thousands of cars to grind to a halt. But what was that substance, and how did it get into the petrol in the first place? Well, to tell us what he's flushed out in the fuel line about this story, Richard Van Noorden's here from Cambridge-based Chemistry World magazine. Richard, what have you found out about this story?
Well, Chris, the culprit was silicon. Silicon in the petrol was causing the cars to judder to a halt. Slightly confusingly, though, it probably wasn't the element silicon as the silvery grey semi-metal that's
you find in
used
computer
in
chips and things.
Yeah, that wouldn't have got into the petrol. It's not soluble in petrol. What actually happened was that people who were testing for silicon found the presence of silicon atoms in the petrol, and the way you do that, it's a bit like your old school flame test. You heat up the petrol, and each atom gives off a characteristic wavelength of light, and you get that colour that's characteristic of silicon.
Because this is how people work out what is in, say, the sun. If you look at the sun's spectrum, you can work out what elements there must be in the sun and in roughly what quantities, because you get light of a very characteristic wavelength coming off.
Exactly. So sodium street lamps give off that characteristic sort of orangey kind of colour.
So, I won't ask you what colour silicon gives off, but why was the silicon in the petrol? Do we know?
We don't actually know why the silicon contaminated the petrol. It shouldn't be in petrol. As silicones, which is when the element silicon combines with oxygen to form long SiO, silicon-oxygen chains with carbon and hydrogen hanging off the end of the silicon, these kind of polymers called silicones can be gel-like, rubbery. They're used
it's bath sealant, isn't it?
Yeah, used also in breast implants, used as lubricants, used as greases. So it's very likely that that, which is soluble in petrol, caused the cars to judder to a halt. Because when the silicones burnt as the petrol was combusted, the hydrocarbon bits, the carbon and hydrogen atoms, were burnt off, leaving silicon and oxygen, silica, which is, of course, sand.
So you made
glass.
Sand in your engine?
So you made sand. It's going to come out as a kind of whitish deposit, and that will clog up the oxygen sensors in the engine. And the oxygen sensors just gave up. They said, look, we're controlling the flow of fuel, and we're being clogged up, so we're going to give up, and your car is going to judder to a halt, I'm afraid.
So presumably only some cars which would have had high-tech oxygen sensors like this would have been affected?
Yeah, it looks like older cars actually carried on okay, despite the fact that
they had an engine full of
forming.
sand.
They had an engine full of sand, but they carried on.
Are there any fuels in which you would normally place silicones?
Yeah, you would put silicones in diesel, where they're anti-foaming agents, so they stop the diesel literally foaming up as you're pouring it in. But you should never have it in petrol. Clearly,
so why don't they form sand in a diesel engine, then?
Well, diesel's not combusted by sparks in the same way that petrol is. In diesel, you use pressure, and it also ignites, whereas in petrol, you're using a spark to burn off the carbon and hydrogen.
But that shouldn't make a difference to whether there's some heat there that can burn silicon and react it with oxygen, surely?
Well, as far as... I'm not exactly sure of the answer to that question, Chris, but I know there isn't that problem in diesel.
Maybe it's just because diesel engines are so robust they'll burn anything. What do you think, Dave?
I guess if a diesel engine doesn't have an oxygen sensor, it's just like an old-fashioned petrol engine, so it would just keep on going. There's nothing to gum up.
Sure. And so basically they've now got to the bottom of, if we think it's silicon, it got into the petrol and shouldn't have done. Is there any way in which we can prevent this happening again?
Yeah, well, one of the problems with finding out that it was silicon was that the standard test for petrol doesn't include a test for silicon, because it shouldn't be in there. They test for all the additives in petrol, lead and copper and so on. So Harvest Energy, who are one of the suppliers to the supermarkets, that like Tesco's, that the faulty petrol came from, they say they're going to now include a standard test for silicon in the petrol whenever they check it. So there's obviously a quality control. How should we check our petrol issue there?
Has it ever happened before, Richard?
As far as we know, not in the UK, but intriguingly, according to the American oil company Chevron's website, used toluene, which is a solvent from a manufacturing process containing soluble silicon, has apparently found its way into gasoline, as the Americans call petrol, and again fouled up oxygen sensors. Now, that's on our website, and when I checked this with a specialist from the American Petroleum Institute, he couldn't remember details of that, so I'm just throwing this out. Nonetheless, I've had people say this to me, that it has happened in America, and somehow recycled toluene with silicon in caused the problems and got into the petrol. Now, of course, I don't know if that's happened here, and no doubt in the next few weeks we'll find out what actually has happened.
Thanks, Richard. That's Richard Van Orden, who is from Chemistry World. They're based in Cambridge. They're from the Royal Society of Chemistry, and you can find out more about that story, the article that Richard's written, on the Chemistry World website. It's at chemistryworld.org.
Just a quick update now on our teaser question. Now, remember, our teaser question is, how many 1 kilowatt bar heaters would we need to replace the sun with in order to get the same heat out? We've had plenty of answers in so far. A couple of new ones. Mark in Bletchley says 100 billion trillion, give or take a few. And Negin in London says 10 to the 20, so 10 with 20 knots on the end.
Got some more for you here, Phil. Graham's in Leiston. He says the answer is 60 trillion. And Charlotte in London thinks our answer is 3 times 10 followed by 23 zeros. Now, I've got a question here on The Naked Scientist. Colin's in Norwich, he says, I want to know whether anything else other than our moon gets eclipsed, such as stars or other planets, and what's actually happening when we have an eclipse, Phil?
Yeah, well, OK, what happens when you get an eclipse is that, or with the eclipse of the moon, is that the Earth passes exactly between the sun and the moon. So basically the Earth's shadow is cast on the surface of the moon, which is why you get that dark colour going across the surface. And it's sort of a reddish colour, basically because you're getting a little bit of light filtering round the edge of the Earth through the atmosphere. And the atmosphere lets red light get through better than blue light, so you get kind of a reddish tinge to the moon. And yet other things do get eclipsed, as it were. Actually, as it happened, well, with the sun, obviously the sun gets eclipsed. That's when the moon passes exactly between the Earth and the sun. Actually, the day before the lunar eclipse, actually we got an occultation of Saturn, which is where our moon passed exactly between us and Saturn. So Saturn disappeared out of view. And you get the same effect from stars and other planets. And actually they can be really useful scientific things to watch. You can find out about atmospheres of planets by watching the stars vanish behind them as a planet.
Someone did that recently, didn't they? They managed to see the first planet that's around a star not in this particular neck of the woods, not our own sun, but in a distant galaxy. They saw this happening and managed to work out what the atmosphere of that planet was.
Yeah, absolutely, and that's actually a really good way to detect a planet around another sun, is as the planet passes in front of that other star, it blocks out a little bit of the light and it goes slightly dimmer for maybe a few hours, and we can actually see that from the Earth sometimes and actually work out there's another planet orbiting around another star somewhere.
Thanks, Phil. Dave, got a question here. This is from someone called David, who says, we're using electric chargers to charge phones and torches and things. Once the product is charged, does the charger switch off, or does it carry on using the same amount of electricity until you switch it off?
They will carry on using some electricity, but it will be significantly less than it would be using while you were charging the phone or whatever, because they're not made perfectly. And if you don't draw any current, they still use some just to heat themselves up, and you get losses in places. But it's quite small, maybe less than a fifth of a watt or so for one charger.
But in terms of what Al Gore's going on about with climate change and all that kind of thing, and we're coming to that in a second, the idea that if you have lots of people everywhere just saying, oh, it's a tiny amount of electricity, it doesn't matter. If we all turned our things off of standby and unplugged our phone chargers when the phone's not plugged in, then we could actually make a difference, I suspect.
I saw a calculation of this, and the guy who did the calculation reckoned it would be 1/100% of the power which the UK uses if everyone took their phone chargers off as soon as they finished charging their phone.
It's all very well to say that's a small number, but the average coal-fired power station for over a few hours pumps out 3,000 tonnes of carbon dioxide. That's a lot, isn't it?
It would make a difference, but I think if everyone went to the shops one less time in a year, it would be better.
Thanks, Dave. In a second, we'll be catching up with what's going to happen at the Cambridge Science Festival this week with Nicola Buckley. That's all on the way. And we've also got our teaser running, tickets to see Al Gore, not in concert, but talking about The Inconvenient Truth, the story about climate change here in Cambridge on the 26th of March. We've got 2 tickets to give away. If you can tell us how many electric 1 kilowatt bars would you need to put in the sky to replace the sun if we wanted to replace the sun with a big electric fire? Closest answer is going to win. But right now, if you're a budding writer or broadcaster, there's an opportunity to showcase your journalistic talents and perhaps break into the mainstream, and that's thanks to a competition that's being run by Cambridge Research UK. And with the inside story, here's our own Dr. Kat Arney.
Hi, Chris. This is an announcement for all you junior news hounds out there. It's a new science writing competition being run by Cancer Research UK. I'm here with Julie Sharp from the charity to find out more.
Well, we're inviting all 14 to 16-year-olds to enter our competition. It's called Sci News, and we want all those budding science reporters to write a 300-word article about a piece of medical or health research that interests them.
So what sort of stories should people be looking for?
You've got to think about your audience. Is the story going to be of interest to them? So do a bit of thinking carefully before you choose your story. You really want something that's going to grab people's attention and excite them or interest them. Tell them something they didn't know about before.
Does the story have to be about cancer?
It doesn't have to be about cancer, but we would like it to be about something related to health or medicine.
Where can people find out more?
Well, we have a website for the competition. It's www.scinews.org.uk. There's also some handy tips on writing a story, what makes a story newsworthy, and there's details about the prizes and our judges.
What are the prizes people can win?
Well, the prizes for the winner, they get a year's subscription to the BBC Science and Technology magazine Focus. They also get the chance to read their news story on our future podcast, and they get to spend a day with our press office. All the winners will also get a science goodie bag, which contains some science books and some Cell Top Trumps.
So if you're aged 14 to 16, then get writing, because the competition closes on April the 30th. That's all from me, and I'll be back in the studio soon. So see you then. Back to you, Chris.
Thank you very much, Kat. And if you feel like putting pen to paper in Dr. Kat's competition, that web address again, it's www.scinews, that's scinews.org.uk. And I've got an email here from Stephen Whitty. And witty he certainly is, because he says, a colleague's invented the relative diet. When it's her turn to bring in bagels, she brings in a lot. She wants to be thin by comparison to the rest of us, it seems.
The Naked Scientist Podcast, brought to you by thenakedscientist.com.
It's The Naked Scientist with Chris and Dave and Phil, and we're taking your science questions if you want to ask us anything. 08459 25 2000. But first, let's head over to Nicola Buckley, who is the organiser for one of Cambridge's biggest annual events, and that's the Cambridge Science Festival. Hi, Nikki. Thanks for coming in.
Oh, you're welcome.
Now, what's the Cambridge Science Festival sort of aiming to achieve? Why are you doing this?
It's all part of National Science and Engineering Week, and we're aiming to provide something for everybody, all ages. We're really interested in getting young people studying science and technology, but we're after their parents as well. We really want to get everybody involved in what's going on at the university and beyond.
So how many people will turn up to something like this?
We're expecting 20,000 visitors.
All in one day?
No, over 2 weeks.
Okay.
Have. We'll be seeing something like 10,000 visitors next Saturday, 17th of March, in Cambridge, when we're opening about 40 different events all in the centre of town. So it's a very action-packed day, I have to say.
Is it just aimed at science geeks like me, or would the average member of the public really appreciate it?
Well, we were in the Grafton Centre yesterday, the shopping centre in Cambridge, with a 5-foot-high robot handing out programmes. And I tell you, we got rid of about 800 programmes because people are seriously keen. They're going, what is going on? And we sell it, well, come meet some robots, come and get some hands-on science with Crash Bang Squelch, the Chaos Group, and people are kind of intrigued, and they think, I want to be part of that.
Why do you think we need this kind of event? Because we never used to have science festivals and all that kind of thing. So why is it so important now?
Oh, I think it's good. You have literary festivals, you have comedy festivals, and I think science deserve their own festivals as well. I think it's a showcase for science events that go on the rest of the year as well. In fact, there are many museums where you can get this kind of learning out of school throughout the rest of the year. But I think everybody needs a highlight. They need some way of finding out what some of the great things are that you can access in your own town, ways to enhance your learning that you might get in school with some of these facilities that might be available through a university or through a museum.
So come on then, whet our appetite. What are some of the really fun and squelchy, funky things we're going to see? You mentioned Crash Bang Squelch. That sounds intriguing. Tell us a bit about that.
Yeah, well, the students at Cambridge Hands-On Science, they'll be doing 50 fantastic hands-on experiments, extracting DNA from kiwi fruit, building bridges. We've got lots of creepy crawlies for you to meet. We've also got a Bottle Your Own Genes event, which is very popular, where the kids are taking cheek swabs and going away half an hour later with a little curl of their own DNA in a necklace.
So you can make your own DNA?
Yeah, it's pretty good.
Okay, and so where does this all kick off and when?
It all kicks off at 10 o'clock on Saturday, 17th of March, down on the Downing site and the new museum site at the University of Cambridge. If you visit our website at cambridgescience.org, all the details are there.
And how much is it going to cost people?
It's absolutely free. Almost the entire festival is entirely free. There are a couple of theatre performances that are charged for, but this is a fantastic free day out for all ages.
Nikki, thanks very much. So I can thoroughly recommend it. We're going to be there on the launch day on Saturday. That's Saturday coming up. So if you can make it to Cambridge and come and see us, we'll be there. The Naked Scientists promoting the Cambridge Science Festival. Thanks, Nikki. Phil.
Just a quick reminder now about the teaser question this week. It's how many bars of electric fire would you need, 1 kilowatt bars, to replace the sun with and get the same heat output? We've had loads of answers in so far, ranging from 15 million to trillions of trillions of trillions.
And up for grabs, if you get the closest answer, we've got 2 tickets, kindly donated by Nikki, who you just heard there, to go and see Al Gore, who's speaking in Cambridge, and it's going to be about the science of climate change. So well worth having, but if you're not keen on Al Gore, then we'll try and dredge you up a mud-powered clock instead.
Fancy listening to The Naked Scientists in your bed, on your way to work, or even at work? Why not subscribe to our podcast? For more information, visit nakedscientist.com/podcast.
It is The Naked Scientist with Dr. Chris, Dr. Dave and Dr. Phil. Connor's in Tillingham. Hi, Connor.
Hello.
What can we tell you about this evening?
Yes, could I just ask, please, is there any actual bone in dinosaur fossils?
Oh, that's a fantastic question. And in fact, I know the answer to this because I met a lady who reckons the answer is yes. Her name is Mary Schwartz, and she works in America, and what she did was an interesting sort of accidental discovery. Most of these discoveries, when you make amazing leaps forward, are usually mistakes or accidents, a bit like Alexander Fleming with his penicillin. What she did was she was getting some fossils and she wanted to get rid of some of the mineral from the fossil in order to make examining it easier. So she put the fossil, a piece of dinosaur bone, into some demineralizing solution, the idea being to sort of slowly remove some of the hard part to leave it a bit softer. And when she came back, having accidentally left it in for longer than she anticipated, she found that there was this matrix of material left behind. And when you look very, very closely at it, it looked like she could see individual blood vessels, and inside the blood vessels she could see cells, blood cells potentially. Oh, right. And so what it looks like is that it's not just completely replaced by permineralization. In other words, you've got minerals put in place of organic tissue. It looks like there may be a sort of halfway house, and it will obviously depend on the age of the bone and the degree of preservation, but it may be that there is real tissue locked up in there as well.
Fantastic.
Definitely with some kind of creatures which are made out of calcium carbonate, which is stuff which makes up most limestone, that definitely gets preserved as is. Because you get creatures like trilobites. I don't know if you've ever seen them. They're little kind of scuttly things that like huge earwigs, maybe possibly not earwigs, the ones which really like earwigs anyway, with lots and lots of legs. And they've actually looked at the eyes of these things, and in some of the fossils you can actually see that because the eyes are actually made out of little bits of calcium carbonate, and the way at which the crystals are aligned means that the eyes would work. If it had been aligned in any other direction, it would see many images. So they can be fairly sure that that's the same crystal as it was when it was living and crawling around.
Great question, though. Thank you very much, Connor, for that.
Thanks very much. Right, bye-bye.
Good to have you on the programme. Right, also this week, scientists have found a way to produce, this is really interesting, silicon replicas of microscopic marine organisms, and they're called diatoms. They're tiny algae, and they have a little shell made of silica, and that's another word for silicon dioxide. It's the same material that makes up sand and glass, and what was finding its way into people's engines when they used the fuel that Richard was talking about earlier. But by turning them into pure silicon, they could also hold the key to producing a new class of extremely sensitive gas detectors. And to explain how that works, Ken Sandage, who's made this discovery, is on the line from Georgia Institute of Technology. Hi, Ken.
Hello.
Thank you for joining us. Now, tell us, how does this work, and why have you decided to convert algae into silicon in the first place?
Okay, the way this works for the silicon type conversion process is through a reduction process, as you can imagine. When you take silicon dioxide and convert it to silicon, that is a reduction process. And so the way we've conducted this in the paper that just came out recently is by using a reducing agent that can be operated at very low temperatures, much lower than the conventional reducing agent for converting silica sand into silicon. And so we use magnesium gas, which can be used as a reducing agent for that reaction at temperatures as low as 650 centigrade. That's important because the conventional way that you reduce silicon dioxide into silicon is through the use of carbon as a reducing agent.
So the carbon literally steals the oxygen off the silicon dioxide and turns it just into pure silicon. But the problem being, of course, that if you try and do that, the temperature you're doing it at is so high that you melt the tiny structures.
That's right, and so it's impossible by a carbothermal reduction process using carbon to retain the structure of the silica in the silicon you produce, because the silicon is a liquid at the temperatures required for that process.
But why did you decide to do this in the first place? Because it's not the most obvious thing to everybody why you should want to go and turn algae into silicon replicas of themselves.
Well, there's sort of two parts to your question that I can answer. The first is why make any kind of a conversion or why conduct any kind of a conversion process with diatom, silica, and why silicon in particular? Well, the answer to the first question was really just a fortunate coincidence. I had been on sabbatical in Germany in 2000 in Hamburg, Germany, as a Humboldt Fellow, and I happened to run into a marine biologist, Monica Schoenwalder, who was working at the Alfred Wegener Institute for Marine and Polar Research. Turns out the Humboldt Foundation likes to have Humboldt scholars, see Germany, see the cultural aspects of Germany. So we were on a bus together, and I just happened to sit next to her one day on the bus, and she had this book that was showing the elegant structures of diatom microshells. which I hadn't really known much about, and she started describing this to me. Well, it turns out, while I was in Germany, I was working with Niels Clausen, another ceramics person like myself, and we were working on ways of doing exchange reactions. Niels and I both had developed different approaches, but I never thought of using those approaches on microscopic things. We were working on macroscopic structures, and suddenly it was like a eureka moment where I realized, geez, we could be using these same reactions that we've been conducting, but on microscopic structures. What's fantastic about diatoms is the amazing precision and massive scale on which they can produce their shells. They're, in fact, genetically encoded, every diatom species, that is, to make a particular shape, and that shape is preserved with high fidelity upon biological reproduction.
So you could literally pluck one that you thought was most appropriate for your causes, grow that to very high levels in just a tank in the lab, and then you've got an endless supply of it almost.
Absolutely, and so that's really a unique and very attractive characteristic of nature in general, the ability of nature to mineralize structures in very elegant fashion, very, very precise and intricate fashion, and to do it on a massive scale.
So how do you think? Sorry to interrupt you, Ken, but I'm a little bit short of time. But how do you think you could use them for this gas sensing approach? How did you discover that?
Well, we had been converting diatoms into other materials for gas sensing, titanium oxide, for example. And we thought about doing this with silicon because silicon can be used for other gases than we were using titania for. And so it's well known that planar porous silicon can be used as a gas sensor for nitric oxide, for ammonia, for water vapor. And we thought we'd use diatoms because they have a very open and porous structure. And in fact, when we converted the silicon dioxide to silicon, it became much more porous. And so because of that, its high surface area and open porous structure, it's a very sensitive gas sensor, and it's three-dimensional. It's not just a planar structure, but it's an open three-dimensional structure, and that turns out to be very attractive for very sensitive and very rapid gas detection.
And which gases can you pick up with it?
Well, in the paper that we published recently was nitric oxide. Nitric oxide, NO, is of a concern. It's a standard pollutant, or a common pollutant from internal combustion engines. But in addition to nitric oxide, I think we can also look at things like ammonia and water vapor, hydrochloric acid, and some organic materials too, some organic vapor species, methanol, ethanol, acetone, etc. And so I think there actually are a family of gases that we can detect with these types of sensors.
It's amazing how nature has a habit of providing you with the answer. Ken, thank you very much.
You're welcome.
It's Ken Sandage from the Georgia Institute of Technology who's found how to convert these tiny marine algal species, which have a little silica shell, into a silicon replica of themselves and then use those as gas sensors.
Another reminder now for your science question this week. How many 1 kilowatt bar heaters would we need to replace the sun, actually up in space where the sun is? We've got another answer in here from Mike in Massachusetts, USA, and he says it would be 510 million bar heaters, and actually works out it would cost about $87 trillion to run those for 1 hour. So quite a lot of money to replace the sun with.
Just in case you missed it, earlier in the show we asked you to mix some vinegar and some bicarbonate of soda together in a beaker and then pour the gas that this produces through the beam of a torch that's pointing at the wall. What do you see? Well, to reveal all, we're back to Dave, Derek, Ellie and Terry to find out what happened when they tried it.
Hello there, welcome back to Castle Manor Business and Enterprise College in Haverhill, where we're still here with Terry and Ellie, and of course Dave, who has been setting up the experiment. And Dave, we've basically got our stuff set up again, so we can do it. So would you just care to instruct Terry and Ellie just to kind of get it all ready again?
We're going to have to make some more carbon dioxide. So Ellie, could you pour a load of vinegar in the cup full of bicarb?
OK, so in case you've just joined us, basically we've got a bit of bicarbonate of soda in the bottom of a pint glass, and Ellie has just poured some vinegar on there. And just to remind us again, Ellie, what happens when we do this?
There are lots of bubbles.
And it also stinks. So there we go, but we'll live with that. And we're now imagining that's full of carbon dioxide. Next.
Now, Terry, could you take this torch and shine it sideways at the wall, a nice white piece of wall? That looks good.
OK, and I think we need to kill the lights here now. So kill the lights. Hey, very good. That's all very synchronised. OK, and now...
Now, Ellie, can you pick up that glass and pretend to pour it in front of the light?
And tell us what you see.
I can sort of see something pouring.
OK, I mean, that's only on the shadow, though. Can you actually see anything pouring, in reality?
No.
OK, yeah. I mean, what we saw there was a kind of a wispy shadow shape kind of coming from the lip of the glass when we poured, but actually we could not see anything coming out of the glass. OK, and is it pouring straight down as well? What direction it's going in?
going kind of sideways.
Yeah, exactly. So it kind of gives the impression that whatever's pouring out isn't particularly heavy, I suppose, because it's not dropping straight downwards. So there you go. We have seen the invisible. Basically, something is coming out of that glass, and the light is allowing us to see it, and we need to know what that is. So, Dave, what is going on here?
Well, now the carbon dioxide which you produced is a gas which is slightly heavier than air. So when you tip the glass up, it'll pour downwards. Now, when the light from the light hits this, light goes slightly slower in carbon dioxide than it does in normal air. So when the light hits it, the light hits the carbon dioxide, it bends slightly. So in some places, it'll get an extra bit of light. In other places, you get a little bit of less light. So you get shadows and extra bright places behind the carbon dioxide. So you can see the pattern on the wall.
OK, so we've got light going through air all the time, which is just what we see all the time, and so that's our normal state of seeing. But then when we introduce this carbon dioxide, it does make the light kind of travel slightly differently, bend slightly differently. Have you got an example for us?
It's the same thing as have you ever seen like light and dark patterns on the bottom of a swimming pool?
Yeah.
Right, OK, fair enough. Yeah, what about that?
Well, the move with the waves on the top. That's where the light's gone into the... when lights come down, in some places it's been bent one way by one side of a wave. In other places it's been bent the other way by the other side of the wave. So you get, again, areas of lighter than they should be and areas that are darker than they should be. So you get these strange patterns on the floor. OK, and you've also got this glass here. So how does that tell us what's going on here? And you get a similar thing if you put a transparent glass up in front of the light. You'll see really dark patches and light patches, just depending on little distortions inside the glass.
Yeah, so what Dave's doing is just as if the carbon dioxide was pouring in front of the beam. We've now got a glass which he's just placed right in front of the beam. And, of course, this glass is completely transparent. It's only made up of transparent material, but it actually creates a shadow because of the shape of it, I suppose. Is that why it bends the light?
Because it's not quite flat. If the light hits it at an angle, it will get bent slightly.
Yeah, OK, and I suppose the carbon dioxide, the shape of that when it's in the air, is that also not flat?
It'll be like a sort of a tube coming down, mostly.
Yeah, exactly. So if you imagine pouring something out of a glass and it kind of goes downwards in a tube, and that's what's happening with the carbon dioxide. Well, hey, OK, there we go. So, Terry and Ellie, we've managed to kind of let you see the invisible. However, do you think this is actually magical? Does that work for you, Ellie?
Yeah, I think it's magic.
Well, OK, well, it's actually science, but we quite like hearing that because, what do you think of the experiment then, Terry?
I thought it was really good because I never knew that the carbon dioxide poured like that.
Yeah, no, that's right. It being heavier is actually quite strange, isn't it? Because often with gas as well, you kind of think of it going up, when you boil some water or something and the steam goes up. But carbon dioxide, there you go, we've shown it's heavier. So, fantastic. All right, then, the smell has also receded, which is great. So, I think Haverhill will be fine. So, there we go. That's all from here, and we'll be back to the studio, and we'll see you next time. Goodbye.
Thank you very much, guys. Next time, we'll be investigating how you can make a bottle of liquid turn to ice in front of your very eyes. And to do it, you're going to need an unopened, pre-chilled bottle of fizzy drink, some ice and some salt. Or you can recruit the help of your local pub landlady. And in fact, we'll be nipping off to the Flying Pig next week. Phil.
How many bars of an electric bar heater would you need, 1 kilowatt bars, to actually replace the sun up in space? And the answer actually is that the sun generates 10 to the 23 kilowatts of energy. So that's 1 with 23 noughts on the end. Or that's 3 times 10 to the 23. So 3 with 23 noughts on the end. So that makes 300 billion trillion electric bars that you would need. And this week's winner is Charlotte in London. She actually got the answer spot on, 3 times 10 to the 23. And she's won tickets to go see Al Gore talking about climate change and his film The Inconvenient Truth in Cambridge on the 26th of March. Well done, Charlotte.
David is in the Shetlands. Hi, David.
Hey.
Listening to us up in Scotland. What would you like to know about?
Well, what I was wanting to know, if you excuse my voice, I've got a bit of a cold here, is what actually generates the heat within the body? I mean, is it the friction of the cells, the blood cells together, or what?
Well, the answer to this question is it's all down to chemistry. So our body runs chemical reactions in every single one of our cells, and those chemical reactions do things like burn glucose, they burn fats, and the consequence of that is that they produce energy. The energy they produce is called ATP, and that ATP, adenosine triphosphate, then gets used in various other chemical reactions in the cells. But in the course of making that ATP, and also in the course of using that ATP, energy in the form of heat is liberated. So if you take a muscle as an example, muscles turn about 20% of the energy that they use into useful movement, and they waste about 80%, and that wastage is literally just heat. So as blood goes through a muscle, it gets warmed up by the active muscle and taken back into the body. Also, other organs inside the body, like the liver, that's producing enormous amounts of heat because it's chemically very active. The kidneys, similarly, the heart, and also don't forget the brain. Your brain accounts for about 25% of all of the oxygen that you burn in any given second in your body, and therefore the brain is producing enormous amounts of heat. So in other words, it's all down to chemistry. And some organisms, like us, are warm-blooded, and that means that we sustain a certain metabolic rate. We burn energy just to keep our bodies warm. Other animals are cold-blooded. They burn energy in just the same way we do, but they don't have a mechanism for staying at the same temperature like we do. So they're things like lizards and frogs, and they have to go and sit on warm rocks to heat up and get their chemical reactions running fast enough to give them the energy that they need to get through a day. Anyway, great question. Thank you very much, David. And unfortunately, we've now run out of time, so that's it for this week. We're back at the same time next week with a Best of the Fest from the Cambridge Science Festival, and we'll be answering all your science questions with a special festival phone-in. So if you've got a problem and you don't know how to solve it, just ask the Naked Scientist. That's chris@nakedscientist.com. That's the address you need to write to. Anyway, for more science news in the meantime, then do give the Nature podcast a listen. That's at nature.com/nature/podcast. And finally, to wrap up, some very big news now, which is that later this week, the Naked Scientist website's about to undergo a total body makeover, and we reckon you're going to love it. So give it a look. It's at nakedscientist.com later on this week, and especially we think you'll like our new forum, nakedscientist.com/forum. Please take a look and tell us what you think. Thank you very much for listening in the meantime, and thank you also to Dr. Dave and Dr. Phil, to Richard Van Norden and Nikki Buckley, who contributed this week, and also to our producers, Petro, Sabina and Azzy. Thanks for listening, and until next time, goodbye!